Hi everyone. Today we're going to study Euclid's division algorithm. Let's begin with Euclid's division lemma. Given positive integers a and b, there exist unique integers q and r satisfying a equals bq plus r. R is greater or equal to 0 but less than b. The a is the given integer, b is the divisor, q is the quotient, and r is the remainder. Now let's proceed to Euclid's division algorithm. Euclid's division algorithm is a technique to compute the highest common factor, or HCF, of two given positive integers. To obtain the HCF of two positive integers, say C and D, with C more than D, follow the steps below. Step 1. Apply Euclid's division lemma to C and D. So we find whole numbers Q and R such that C equals DQ plus R. R here is more than or equal to 0 but less than D. Step 2. If R equals 0, D is the HCF of C and D. If R is not equal to 0, apply the division lemma to D and R. Step 3. Continue the process till the remainder is 0. The divisor at this stage will be the required HCF. Note that given two positive integers C and D with C more than D, then C equals DQ plus R. We say that R is more than or equal to 0 but less than D. This algorithm works because HCF of CD equals HCF of DR. Example 1. Use Euclid's algorithm to find the HCF of 4052 and 12576. Step 1. Since 12576 is more than 4052, we apply the division lemma to 12576 and 4052. That means we divide 12576 by 4052. So we get 12576 equals 4052 times 3 plus 420. Step 2. Since the remainder 420 is not equal to 0, we apply the division lemma to 4052 and 420. So we have 4052 divided by 420. So we get this equation. 4052 equals 420 times 9 plus 272. We consider the new divisor 420 and the new remainder 272. So we divide 420 by 272. So we get this equation. 420 equals 272 times 1 plus 148. We consider the new divisor 272 and the new remainder 148. So we divide 272 by 148 and we get this equation. 272 equals 148 times 1 plus 124. We consider the new divisor 148 and the new remainder 124. So we divide 148 by 124. So we get this equation. 148 equals 124 times 1, then plus 24. We consider the new divisor 124 and the new remainder 24. We divide 124 by 24. So we get this equation. 124 equals 24 times 5 plus 4. We consider the new divisor 24 and the new remainder 4. We divide 24 by 4. Then we get this equation. 24 equals 4 times 6 plus 0. The remainder has now become 0, so our procedure stops. Since the divisor at this stage is 4, the HCF of 12,576 and 4,052 is 4. To summarize, this is what we did. This 12,576 divided by 4,052. We get this equation. 12,576 equals 4,052 times 3 plus 420. Now, this 4,052 divided by 420. So we get the second equation. 4,052 equals 420 times 9 plus 272. The remainder is not 0, so we continue the process. 420 divided by 272. We get the third equation. 420 equals 272 times 1 plus 148. Then we divide 272 by 148. We get the fourth equation. 272 equals 148 times 1 plus 124. Then we divide 148 by 124. We got the fifth equation. 148 equals 124 times 1, then plus 24. Then we divide 124 by 24. We get the sixth equation. 124 equals 24 times 5, then plus 4. We divide now 24 by 4. We get the last equation. 24 equals 4 times 6 plus the remainder 0. We stop here because remainder is 0. And we say HCF of 12,576 and 4,052 is 4. Example 2. Show that every positive even integer is of the form 2q, and that every positive odd integer is of the form 2q plus 1, where q is some integer. Let a be any positive integer and b equals 2. By Euclid's algorithm, we write a equals 2q plus r. For some integer q more than or equal to 0, and r, the remainder, equals 0, or the remainder r equals 1, because r is more than or equal to 0, but less than 2. So we write a equals 2q, or a equals 2q plus 1. If a is of the form 2q, then a is an even integer. Also, any positive odd integer is of the form 2q plus 1. Example 3. Show that any positive odd integer is of the form 4q plus 1. or 4q plus 3, where q is some integer. Let a be a positive odd integer. We apply the division algorithm with a and b equals 4. Since r is more than or equal to 0 but less than 4, the possible remainders are 0, 1, 2, and 3. That is, a can be 4q, or 4q plus 1, or 4q plus 2, or 4q plus 3, where q is the quotient. However, since a is odd, a cannot be 4q or 4q plus 2, since they are both divisible by 2. Therefore, any odd integer is of the form 4q plus 1 or 4q plus 3. Example 4. A sweet seller has 420 kaju barfis and 130 badam barfis. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. What is the number of barfis that can be placed in each stack for this purpose? We are going to find the HCF of 420 and 130. This number will give the maximum number of barfis in each stack, and the number of stacks will then be the least. The area of the tray that is used up will be the least. By Euclid's algorithm, we divide 420 by 130, and we have this equation. 420 equals 130 times 3 plus 30. The remainder is 30. It is not 0, so we continue the process. 130 divided by 30. We get the second equation. 130 equals 30 times 4 plus 10. The remainder is not 0. We continue the process. 30 divided by 10, we get the third equation. We have 30 equals 10 times 3 plus 0. Since the remainder is 0, we stop here. So, the HCF of 420 and 130 is 10. Therefore, the sweet seller can make stocks of 10 for both kinds of barfi. Hi everyone. Today we're going to study the fundamental theorem of arithmetic. Every composite number can be expressed, or we say factorized, as a product of primes. And this factorization is unique, apart from the order in which the prime factors occur. That is, given any composite number, there is one and only one way to write it as a product of primes, as long as we are not particular about the order in which the primes occur. In general, given a composite number x, we factorize it as x equals p sub 1 times p sub 2 times up to p sub n, where p sub 1, p sub 2, up to p sub n are primes, and written in ascending order. If we combine the same primes, we will get powers of primes. Example, we have this number 32,760. We can factorize it into like this. We have 2 times 2 times 2 times 3 times 3 times 5 times 7 times 13. We have the prime factors here. Then we combine all prime factors which are same. We can see here that the factor 2 appears 3 times. So we can write 2 cubed times the factor 3 appears twice. So we write here 3 square. Then we just copy the 5, the 7, and 13. The expression of a number into product of prime factors is called prime factorization method. Example 1. Consider the numbers 4 raised to n, where n is a natural number. Check whether there is any value of n for which 4 raised to n ends with a digit 0. If the number 4 raised to n for any n were to end with a digit 0, then it would be divisible by 5. That is, the prime factorization of 4 raised to n would contain the prime 5. This is not possible because this 4 raised to n we can express as 2 square that is raised to power n. Then we multiply the power 2 by the n. We have now 2 raised to 2n. So the only prime in the factorization of 4 raised to n is 2. So the uniqueness of the fundamental theorem of arithmetic guarantees that there are no other primes in the factorization of 4 raised to n. So there is no natural number n for which 4 raised to n ends with a digit 0. Example 2. Find the LCM and HCF of 6 and 20 by the prime factorization method. Let us write the two numbers 6 and 20. Then we factorize by prime factors. For number 6, we have 2 times 3. For number 20, we have 2 times 2 times 5. We combine the 2 and 2 using powers. We have now 2 square times 5. Then we have the HCF, which is the highest common factor. By definition, we say that HCF is the product of the smallest power of each common prime factor in the numbers. Looking at the prime factors of 6 and 20, we can see that the common prime factor is the number 2. But based on the definition, we will take the smallest power. So the HCF of 6 and 20 is 2 with power 1. HCF is 2. Then we go to LCM. LCM means least common multiple. By definition, we say that LCM is the product of the greatest power of each prime factor involved in the numbers. So for LCM of 6 and 20, we're going to copy all the factors in here to be multiplied together. In case of common factor, we will take the greatest power. So we write here 2 square with 2 as common, and we take the greatest power or greater power. Then we write the factor 3 here. Then we copy the factor 5. We get the product. The answer is 60. This is the LCM. Example 3. Find the HCF and LCM of the numbers 6, 72, and 120 using the prime factorization method. We write the three numbers in here, then we write the corresponding prime factors. For number 6, we have the 2 by 3. For 72, we write 2 cubed times 3 square. For 120, the answer is 2 cubed times 3 times 5. Now let's begin with HCF of the three numbers. We define this HCF, the product of the smallest power of each common prime factor in the numbers. Looking at the prime factors, we can see that number 2 is common, but we will take the smallest power, and that is power 1, to be multiplied by another common factor, which is 3, and we take the smallest power, which is power 1. So this is 2 times 3. HCF is 6. Then we go to LCM of the three numbers. Again, we define LCM as the product of the greatest power of each prime factor involved in the numbers. We will copy all the factors in here. We will write as LCM. So we have 2 cubed. This time, we will write the highest or greatest power times the 3 with power 2 times the factor 5. When we simplify by getting the product, the answer is 360. Hi everyone. Today we're going to study irrational numbers. By definition, a number S is called irrational if it cannot be written in the form P over Q, where P and Q are integers and Q not equal to 0. We have examples here: square root of 2, square root of 3, square root of 11, pi, negative of the fraction, square root of 2 over square root of 3. Also this decimal, 0.1011, 0111, 01111, 0, and so on. For decimals, we say that decimals that are non-repeating and non-terminating are irrational. We have this theorem. Let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. This theorem will help to prove that irrational numbers are not rational. Now we have proof by contradiction. To prove whether a number is irrational, we use a technique called proof by contradiction. Proof by contradiction is a method to prove the statement P by using the double negation law. This method consists of 3 steps. Step 1, we assume that not P is true. Step 2, find a contradiction. In other words, find that not P is actually false, which means the negation of not P is true. Then step 3, conclude that P is true. That is, P is logically equivalent to negation of not P. Let us see this example. Prove that square root of 2 is irrational. Our step 1, we assume that not P is true. Our proposition P here is square root of 2 is irrational. The not P correspond to square root of 2 is rational. So for step 1, we will assume that this is true. If square root of 2 is rational, we can show that square root of 2 equals a over b. This a over b must be in lowest term. It means there is no common factor between a and b, where a and b are integers and b not equal to 0. Further, both a and b cannot be even integers. Otherwise, the number 2 becomes a common factor for both a and b. Now, step 2, let us find a contradiction based from these statements. That is, let us find that not P is actually false, which means the negation of not P is true. What we're going to do here, let us square this equation. The square root of 2 becomes 2 equals a over b when squared becomes a square over b square. Let us cross multiply this b square to the number 2 on the left side, so that becomes 2b square. Or we can write a square equals 2b square. The constant 2 with a b square gives us idea that the square of a is an even integer. Since a square is even, it follows that a itself is even. Given that a is even, we can now represent a equals 2k, where this k is any integer. Now let us solve for b. Let us substitute this a equals 2k to the equation here. The 2 equals a square over b square. This equation now becomes 2 equals the square of 2k over b square. The square of 2k becomes 4k square. Now let us cross multiply b square with a constant 2 on the left side. So we will have 2b square equals 4k square. Let us divide this equation by 2. So we will get b square equals 2k square. The constant 2 on the right side is telling that the square of b is an even integer. Now it follows that b itself is even. It means we found a contradiction. Our computation here tells us that a is even and b is also even. It contradicts our idea earlier that a over b must be in lowest term. We can go now to step 3. We can conclude that p is true. Our p is here. So we say that, therefore, square root of 2 is irrational. This is our final answer. Example 2. Prove that square root of 3 is irrational. Step 1. We assume not p is true. It means we're going to assume that square root of 3 is rational. If so, square root of 3 equals a over b, where a and b, this b not equal to 0, are integers. Also, we say that this fraction a over b is in lowest term. Now, step 2. Let us find a contradiction. By squaring on both sides and rearranging, we will have this new equation. 3b squared equals a square. Let us regard this as equation 1. By this equation, we can see that 3 is a factor of a square. Therefore, a square is divisible by 3. And by theorem, it follows that a is also divisible by 3. So we can write this a equals 3 times c for some integer c. Now let us substitute this value of a to equation 1. So we have this 3b squared equals the quantity 3c that is raised to power 2. Simplifying the right side, we have now 9c squared. Let us divide this equation by 3. So the value of b squared equals 3c squared. And this is now our equation 2. From here we can see that 3 is a factor of b squared. It means that b squared is divisible by 3. And so b is also divisible by 3. Therefore, a and b have at least the number 3 as a common factor. But this contradicts the fact that a over b is in lowest term. This contradiction has risen because of our incorrect assumption that square root of 3 is rational. So we conclude that square root of 3 is irrational. Let's have more theorems. The sum or difference of a rational and an irrational number is irrational. The other is the product and quotient of a non-zero rational and irrational number is irrational. So we have example 3. Prove that 5 minus square root of 3 is irrational. Step 1, we assume that not p is true. It means we're going to assume that 5 minus square root of 3 is rational. If so, this 5 minus square root of 3 equals a over b, where a and b and this b not equal to 0 are integers. Also, the fraction is in lowest term. In some books, they say that a and b are coprime. Now step 2. Let's find a contradiction. Rearranging this equation, we have now 5 minus a over b equals the square root of 3. Now, for the left side value, we're going to combine as a single fraction, and it becomes 5b minus a over b. Since a and b are integers, the fraction 5b minus a over b, that is the left side value, is rational. Also, the square root of 3 is rational. But this contradicts the fact that square root of 3 is irrational. This contradiction has risen because of our incorrect assumption that 5 minus square root of 3 is rational. So, we conclude that 5 minus square root of 3 is irrational. Example 4. Show that 3 square root of 2 is irrational. Step 1. We assume that not p is true. Therefore, we assume that the 3 square root of 2 is rational. If so, this 3 square root of 2 may be expressed as a over b, where a and b, and this b not equal to 0, are integers, and a and b are co-prime. Then step 2. Let's find a contradiction. We arrange this equation and it becomes square root of 2 equals a over 3b. Since the number 3 and this a and b are integers, the fraction a over 3b is rational. And so, the square root of 2 is rational. But this contradicts the fact that square root of 2 is irrational. This contradiction has arisen because of our incorrect assumption that 3 square root of 2 is rational. So, we conclude that 3 square root of 2 is irrational. Hi everyone! Today we're going to study rational numbers and their decimal expansions. By definition, a rational number is a number of the form p over q, where p and q are integers and q not equal to 0. The decimal expansion of p over q is terminating or non-terminating repeating. In some books, they use the word recurring. Let us see this theorem. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p over q, where p and q are co-prime, and the prime factorization of q is of the form 2 raised to n times 5 raised to m. We call this powers of 10, where n, m are non-negative integers. Example 1. Convert 0.375 into fraction and simplify. The given decimal is 0.375. We read this formally as 375 thousandths. We include here the placed value of the last digit, which is 5, the thousandths. By this, we express our decimal as a fraction, just like this. In the numerator, we copy the given decimal without the decimal point. So we have here 375 over 1000, because we have here thousands as the place value of the last digit, which is 5. And then let us express the 1000 into 10 raised to 3. In the next step, we're going to list the prime factorization of both numerator and denominator. In the numerator, we have 3 times 5 cubed. In the denominator, we have 2 times 5, and the quantity is raised to power 3. And then, let us distribute the power 3 of the denominator to each of the factor. So we have 2 cubed times 5 cubed. Next step, let us cancel out common factors and simplify. The 5 cubed is common, so we cancel it out. So in the numerator, we have 3 times 1. So we have 3 over the 2 cubed becomes 8. This is the final answer. Example 2. Convert 23.3408 into fraction and simplify. The given decimal is here, and we read this formally as 23 and 3,408. The place value is 10,000. So we write this as a fraction. In the numerator, we copy our decimal without the decimal point over the 10,000 value, which is coming from the place value of the last digit, which is 8. And then let us express our denominator into 10 raised to 4. In the next step, we're going to list the prime factorization of both numerator and denominator. For the numerator, we have this 2 raised to 6 times 7 times 521 over, in the denominator, this 10 raised to 4 becomes 2 raised to 4 times 5 raised to 4. Then we're going to cancel common factors. The 2 raised to 4 in the denominator is cancelled totally, and there is 2 raised to 6 in the numerator. Cancelling the 2 raised to 4, we have 2 squared that remains in the numerator times the 7 times the 521. So we simplify the numerator as 14,588 over the 5 raised to 4 is equal to 625. This is the final answer. Let us see the other theorem. Let x equals p over q be a rational number such that the prime factorization of q is of the form 2 raised to n times 5 raised to m, or we say power of 10, where n and m are non-negative integers. Then x has a decimal expansion which terminates. This is the reverse process of what we did in the first two examples. Let's have example 3. Convert 13 over 125 into decimal. The given fraction is 13 over 125. We're going to list the prime factorization of the denominator, and that is 5 cubed. Next step, we're going to convert the denominator into powers of 10. The form is 2 raised to m times 5 raised to m. Take note here that we must make the powers equal. In our denominator here, we have 5 cubed. Thus, we need a factor 2, but with the same power, that is 3. So, we multiply the 5 cubed by 2 cubed. Since we multiply our denominator by this value, same value must be multiplied to the numerator. So here it is. Then let us simplify our denominator into the quantity 2 times 5 that is raised to power 3. And then the 2 times 5 becomes 10 that is raised to 3. Simplifying further, the numerator becomes 13 times 2 cubed is 104. The 10 cubed is 1000. Now we are ready to convert this fraction into decimal. For the decimal value, this is what we will do. In the numerator value, we're going to move the decimal point to the left into number of places as there are zeros in the denominator. Our denominator is 1000. So we have here 3 zeros. Our numerator is 104. The decimal point is after the number 4. So we're going to move the decimal point 3 places to the left. So the decimal will be like this, 0.104. This is the final answer. Example 4. Convert 7 over 80 into decimal. Our fraction is 7 over 80. First thing to do is to list the prime factorization of the denominator. 80 equals 2 raised to 4 times 5. Next is, we're going to convert the denominator into powers of 10. Again, we say that the powers, that is m, must be same. There must be two factors, 2 and 5. And here they are. We can see that the power of 2 is 4, while the power of 5 is 1. The power of 2 is more. We need to adjust to the factor 5. So we are going to multiply the denominator by 5 cubed, so that the power of 5 will be equal to the power of 2, which is number 4. Now we multiply our denominator by 5 cubed. It means we should multiply 5 cubed to numerator also. So it becomes like this. When we simplify the denominator, we have now 2 raised to 4 times 5 raised to 4. In the numerator, we have now 7 times 5 cubed is 125. Then we simplify further our denominator. It becomes 2 times 5, and the quantity is raised to power 4. In the numerator, 7 times 125 is 875. The 2 times 5 here becomes 10, that is raised to 4. Simplifying this 10 raised to 4, we have now 10,000. So we have the fraction 875 over 10,000. We are now ready to write this as decimal. For the decimal value, look at the numerator. We're going to move the decimal point to the left into number of places as there are zeros in the denominator. We have 10,000 in the denominator. It means 4 zeros. We're going to move the decimal point of the numerator value 4 places to the left. So the decimal is 0.0875. This is the final answer. Here is another theorem. Let x equals p over q, where p and q are coprimes, be a rational number, such that the prime factorization of q is not of the form 2 raised to n times 5 raised to m, where n, m are non-negative integers. Then x has a decimal expansion, which is non-terminating repeating. Again, in some books, they use the word recurring. Example 5. Convert 1 over 7 into decimal. We can see that our denominator, which is the number 7, is clearly not of the form 2 raised to n times 5 raised to m. Thus, it will not have a terminating decimal. Let us now divide 1 by 7. So, here we go. 1 divided by 7 cannot be. So, we write 0 on top of 1. Then we show the decimal point after 1. That same decimal point we will put after 0 on top in the quotient. Then we will add 0 to 1. This becomes 10. 10 divided by 7 is 1. 1 times 7 is 7. 10 minus 7 is now 3. Then we add 0. 30 divided by 7 is 4. 4 times 7 is 28. 30 minus 28 is 2. Then add another 0. 20 divided by 7 is 2. 2 times 7 is 14. 20 minus 14 is 6. Then we add another 0. 60 divided by 7 is 8. 8 times 7 is 56. 60 minus 56 is 4. Then we add 0. 40 divided by 7 is 5. 5 times 7 is 35. 40 minus 35 is 5. Then we add 0. 50 divided by 7 is 7. 7 times 7 is 49. 50 minus 49 is 1. Then we add 0. 10 divided by 7 is 1. 1 times 7 is 7. 10 minus 7 is 3. Then we add 0. Then we pause in here. Check now that remainders are 3, 2, 6, 4, 5, 1, 3, 2, 6, 4, 5, 1, and so on. Remainders repeat after a certain stage. So, we will have the block of digits 1, 4, 2, 8, 5, 7 repeating also. So, this is the final answer.